Okay, hello, good afternoon, everyone, and good afternoon, Professor Sakwan Char.
Hello.
It's very nice to see you today, and thank you for all attendance to attend the webinar today. So today is our honor to have Professor Sakwan Shah for Department of Mechanical and Aerospace Engineering, Seoul National University, to join our webinar today. And his talk will be on the application of sputtering process for low temperature reversible operation of solid oxide cells. So thank you very much, Professor Shah. So you can start the session right now.
Okay, thank you very much. Okay. Thank you very much for the nice introduction by Professor Rojana. Okay, as introduced, I am my name is here, Seokwon Cha, and then I am currently the professor at the Department of Mechanical Engineering at the Seoul National University. Okay, so thank you for the invitation, and then I hope that you can enjoy my talk even though it's online. Okay, then so today I am going to present the recent research, okay, on the so-called solid oxide cells. And then solid oxide cell means usually there are two types of solid oxide cells, right? The solid oxide fuel cell or solid oxide electrolysis cell. Actually, I'm going to talk about both of them. So when I say the reversible, means this solid oxide cell can operate as a fuel cell and also as a electrolysis cell. Okay, so that's why it's called reversible operation. And then mainly I'm going to discuss about the process of making these solid oxide cells, and then most of the process that employed in the research is so-called sputtering. So it's a physical vapor deposition process, and then I'm trying to operate all these solid oxide cells at a low temperature. So that's the purpose of my talk, and then let's discuss this research maybe about 30 or 40 minutes, and then I can answer your questions. Okay. Okay, so to begin, just a little bit of introduction of the background. Okay, so all you know that when you make the hydrogen, okay, there are maybe so-called gray hydrogen or blue hydrogen or green hydrogen. So people just color, okay, name the hydrogen with different colors. So the gray hydrogen means the hydrogen usually produced by the fossil fuel. So most common way of producing the hydrogen is using the natural gas, and then adding the natural gas with water or steam, and then go through this with some catalyst. We go through reforming process, and then we can generate hydrogen. Currently, this is one of the cheapest method of making hydrogen, even though recently the natural gas price soaring up, so it's very expensive now. So this may not be the cheapest method in the future, but anyway, you can make the hydrogen, okay, with this fossil fuel using mixing with the water, steam reforming. The biggest downside is based on the hydrocarbon fuel, so it generates carbon dioxide, so CO2. Okay, the carbon dioxide is generated, so you have this so-called carbon emission. Okay, another type of the hydrogen, we name it as a blue hydrogen. Okay, it's also based on the fossil fuel, so we make this hydrogen using also the natural gas, so steam reforming. But the difference is we capture the carbon dioxide, right? So it's a method is based on the fossil fuel, but we capture the carbon dioxide and then store them. So it's basically it requires carbon sequestration. So we carbon capture and then storage in the land or cave or in deep sea. okay, or we do the chemical treatment, whatever method we use, and then remove the carbon dioxide. So why it's called blue hydrogen. So basically it's clean, but it requires more energy to capture the carbon dioxide. So it requires energy. Okay. So but still we do not produce any carbon. Okay. So it's blue hydrogen. Another type, the last type of the hydrogen is so-called green hydrogen. So it does not generate any CO2. The easy way of making this green hydrogen is using the electricity and then disintegrate water. So disintegrate water into hydrogen and oxygen. Okay, so it only emits, it produces hydrogen and oxygen. So that's the green hydrogen. But it requires the electricity, water, and then it's called electrolysis. Okay, so it's a water splitting. Okay, and then there is no carbon emission. So the green hydrogen is the one of the final goal. Okay, of the to achieve the so-called net zero emissions. Okay, no emission society. Okay, to achieve the no emission society. The final goal is making the green hydrogen. Okay, so we talked about the so-called electrolysis, splitting of water. The typical electrolysis is represented by 2 or 3, okay, the devices. One is based on the proton exchange membrane. The other is solid oxide membrane, and then basically this is similar to the proton exchange membrane fuel cell or the solid oxide fuel cell. So it has the same the characteristics of the both device. So proton exchange membrane, okay, it operates relatively at low temperature, near the room temperature, uses the platinum as a catalyst, and then using the proton exchange membrane, it splits water into oxygen and then hydrogen, and then we provide electricity, okay, into the electrolyzer. The other type, the solid oxide, okay, electrolyte cell, it's similar to solid oxide fuel cell, but the operating temperature is very high, typically 800 to 1000 Celsius, and then it splits water into hydrogen and oxygen using the electricity. Okay, so these are the major 2 types of cells, and then today I'm going to talk about so-called the solid oxide cell. So this is the focus of my talk today. So it's made of the solid oxide membrane, ceramic membrane. When we talk about the solid oxide cell, okay, so it's like you can 2 types, right? There is a solid oxide fuel cell, or it can be also the solid oxide electrolyte cell. Okay, and then unlike the PMFC, okay, the low temperature proton exchange membrane fuel cell, the solid oxide cells actually same single cell can operate in both ways. One single cell can be a fuel cell, and at the same time, it can be the solid oxide electrolyte cell. So that means it's possible to have the reversible operation. So it's a versatile. When you want to make electricity, you can make electricity out of hydrogen, or if you want to make hydrogen, okay, you reverse the process. You use the electricity and then make the hydrogen. Okay, so in using the solid oxide cell, okay, the so-called reversible operation is possible. So that means you can produce energy or you can store energy at the same time with a single cell. So it's a very versatile. But there are several, or actually lots of issues, okay, on the so-called solid oxide cells. Okay, so some of I'm explaining some of the key issues, okay, that happens in the solid oxide cell. One may be the also on the cathode side. So it's nickel. Okay, when you use nickel, the catalyst on the cathode side. Okay, the problem is this nickel start to deplete. Okay, or in the moves around and then start to deplete. Depletion happens at the catalyst layer, and then also nickel can form some unwanted volatile species, okay, near the electrolyte, which is the zirconia, yttrium stabilized zirconia YSD surface. So there is some change of a physical, okay, property of this metal catalyst, which usually happens at the high temperature, okay, around like 800 Celsius, which is a typical operating temperature of the solid oxide cells. And also in the electrolyte, we also observe some unwanted degradation, which is some intergranular or intragranular pore formation. So originally, it's starts from you make the dense membrane electrolyte with the ceramics, but during the operation of the solid oxide cells, you generate these pores in this electrolyte structure. Also, this happens typically at the high temperature. And also, we have some serious issues with the oxygen electrode, okay, which we typically use so-called the LSM here, LSM material for high temperature around 800 Celsius, or the LSCF, okay, the oxygen electrode at a lower temperature. The problem with these two materials is usually there is this strontium material here exists in this oxygen electrode, okay, usually diffuse strontium or the cobalt diffuse, and then they react with the electrolyte, which is zirconia based, and then they form on some unwanted phase, which basically the breaks down the operation of these solid oxide cells. And also this kind of phenomena, okay, this that phase change and then forming the secondary phase usually happens near something around like at high temperature, around 800 Celsius and over. Okay, and also when you have this diffusion, it changes also the pore structure of the electrode, and then it may change the pores, and then it blocks the pore, and then the open pore is blocked, and then the oxygen or the water, the transport through this pore is impossible. So if you I discussed several some problems of this the solid oxide cells, okay, and then regarding the electrodes and the electrolyte, all these problems basically comes from the operating temperature, high operating temperature of solid oxide cells, like formation of the pores or the formation of some secondary phase materials. All these things happens at high temperature. So what I'm trying to do in my research is basically try to remove all these the problems by simply changing the operating temperature of these solid oxide cells. Okay, so what I'm trying to do is reduce the operating temperature. And another thing that I want to use is I make this very aligned pores, and then improve the transport of gases. Okay, gases in the electrode. So that's the goal of my research presented today. So how do I do it is basically, if you look at the conventional, okay, solid oxide cells or solid oxide electrolyte cells or solid oxide fuel cell, typically made of these the thick ceramic films. Okay, so like a zirconia here, typically of tens of microns, okay, tens of microns thickness, and some millimeter thickness of the electrode structure. And then what I'm trying to do is using some nano pore substrates, so-called the anodized alumina. It's an alumina pore, so you can make well-aligned pores in the alumina structure. And then on top of it, okay, deposit the electrode and electrolyte using the sputtering or the vapor deposition technique, and then make a very thin structure. So by doing this, I can reduce the operating temperature. So that means I reduce the resistance, okay, by thinning, okay, by employing the very thin membrane, decrease the resistance, and then reduce the operating temperature. So this is some example of how this structure is made. and then I'm going to explain some details about the process, how to make this these types of structure. Okay, so the structure looks like this cell. Okay, so starting from the nanopore, the porous alumina support, and then use the typical solid oxide cell, the electrode, which is the nickel, and then made of the nickel metal, and then zirconia YZ yttria stabilized zirconia oxide, and the electrolyte is made of also the yttria stabilized zirconia, and then this oxygen electrode is made of this LSCF material, which was introduced before, and also the mixture with the gadolinium doped ceria, which improves the oxygen conductivity at the electrode. So I will show you all these, basically this electrolyte, and then this the complicated oxygen electrode can be made by the vacuum process. Okay, and then if you do that, this is actually the final result, but you can demonstrate the operation of the reversible solid oxide fuel cell or solid oxide electrolyte cell, electrolyzer cell at the very low temperature, something like 500 Celsius, or even go down to 450 Celsius, which which prevents the degradation of the materials that I explained before in previous slides. Okay, so first I start explain about the process for the electrolyte. So the yttria stabilized zirconia using the sputtering process. Okay, so when we the requirements of the electrolyte, the zirconia electrolyte and the solid oxide cell is we need first a thin layer, but it has to be very dense. Okay, so to achieve that, actually in typical sputtering process, we have to employ some special configuration of the sputtering process, because the normal sputtering process cannot achieve what the like full dense or some crystalline structures that we wanted. So we actually the method that we employed is actually changing the distance, okay, between the target and our substrate. Basically, this is a cell, and then we using the plasma, we the deposit, okay, from our the target material, and then transfer that to our the cells, but through the plasma process. But we have to first control the distance, and then also it turns out that we have to control also the rotation, okay, rotation of the substrate. So rotational speed is important, because we need a dense and then good crystallinity in zirconia electrolyte membrane. So we changed both parameters, okay, at the same time, and we did some experiment. Okay, so there are some previous references, not exactly the same material, but we found some references. Okay, so usually the rotational speed, okay, turns out that changes the film hardness, and then especially the stresses, okay, stresses in the film, because when you rotate, okay, this deposition angles changes, okay, and then we can go faster or slow. It changes the directionality of this film growth. So some common knowledge we know, okay, about this phenomena is that when you increase the rotation speed, okay, usually we decrease the stress. So we can guess, okay, a little bit of higher, but not too high, because if it's too high speed, it's impossible to make to achieve the crystallinity. So we have to figure out some proper rotational speed to have the good crystallinity and also the good density, okay, and then low stress in the film. Okay, the other, okay, parameter we want to control is the distance, okay, between the target and the substrate. Okay, If the distance is too small, okay, usually small, then the impact power of the plasma is large. So the so-called the sticking coefficient, okay, decreases because it's hitting very hard. The atoms from the target hit the substrate in high energy, so sticking coefficient, okay, is small. But if you increase the distance, the sticking coefficient increases. So more materials will stick to the surface in the first bombardment. Okay, so these are the like sort of two like parameters that we want to control, and then actually controlling two parameters at the same time is very difficult process, and then sometimes it's very unclear what effect we will have from this controlling these two parameters. Anyway, we did some systematic the investigation of the two parameters. So we changed the distance from the short to high. Okay, so it's by numbers. Okay, high number, small number. So it's a distance. Okay, and also we changed the rotational speed. Okay, some proper range in a proper range. So it's a low speed versus high speed. Okay, so these things are the what we tried in our sputtering machine, and then we use the RF source, and then we use a target as yttrium and zirconia. This is alloy. We use the RF source, but this is alloy, and then this metal alloy target, okay, actually the oxidize during the plasma process. So to achieve that, we use the oxygen, okay, oxygen plasma environment. So these metal targets, okay, metal targets are turned into plasma, and then they oxidize, and then they deposit into the cell surface, and then form the YSC, the oxide ceramic membrane. Okay. Okay, so here are some observations first. Okay, so like 4 different cases. And then it's somewhat difficult to notice big changes by this SEM image. But you can see there is a tendency of the growth of this the columnar structure. Okay, so there can be some angles, can be like this steep. Okay, just some typical, okay, like this types of steep. The growth angle, okay, growth angle can be shown here, or using some parameters, it's difficult to observe those kind of this growth angle, okay, angle, the direction, growth direction on this columnar columnar film, okay, and also in the surface you can see there is like some small spots, okay, small like grain spots, versus some films are more dense, okay, in this case. Okay, so and then for the property of electrolyte that we want is actually the high density. So we can guess some parameters. Okay, some parameters are more favorable, to make the dense electrolyte. Sorry. And then also we observe the surface quality. Okay, and then it's have some similar tendency from our previous the SEM image. Okay, as you can see, with some better, okay, dense film actually generate, you can see the more smooth surface, basically more smooth surface. So we can guess that also this AFM data sort of confirms our visual investigation by the SEM. And then also crystallinity is very important. So this is the crystal XRD the analysis of all these 4 different films, and also this is a measurement of the density. And then this is sort of also confirms our observation from the SEM image. For example, clearly the visibly dense layer actually has the high density from XRR observation. Also, you can see the crystallinity. Some materials, okay, have some different orientation. As you could see the direction of the crystalline, okay, in the SEM image, okay, on the side, the cross-section image, you have noticed that. Also, that confirms with our the XRD observation, like there is some orientations of the crystallinity, and then when we have this dense film, okay, actually that turns out that that dense film have the polycrystalline structure. So it's more like not really have some certain orientation, but it's a well-formed crystalline, and the grains can be grown using certain processes, okay? certain the condition, okay, deposition condition. So it's a great finding that we can make the structure into grow our structure into polycrystalline films. Okay, so we tested. Okay, actually the best. Okay, the final goal that we want is the operation of the solid oxide cell. Okay, making the electricity or making the hydrogen. Okay, so we tested. Okay, the cells, the electrolyte cell. Okay, the electrolyte. Okay, property of electrolyte. So we typically use the nickel, the steam electrode, and then in this case we are just for the testing the electrolyte. So we use the platinum as the oxygen electrode, and then it turns out that when we have when you have the dense and then this good polycrystalline structure, as we expected, shows the best performance. Okay, as a fuel cell mode, or even in the electrolysis mode. So this is a zero current density. So on your right side is basically we are providing hydrogen and oxygen and then make the electricity. And then you can see it generate up to like 2 ampere, which shows a very high performance even at 500 Celsius. So it's a thin film structure, really works because it's thin at the very low temperature, okay, and stable. And then the left side, basically we're providing water, and then we are making hydrogen. So it's a electrolysis mode. So it's basically the same cell. We simply provide the hydrogen and make the electricity, or we just simply provide water and then make provide electricity, then we make the hydrogen. So it's a single cell, one single solid oxide cell, which can be tested in both directions. So this is what we have tested, and then turns out that we could at least one condition works fine, works great to make a dense electrolyte. And then we can confirm, okay, the property of electrolyte also in our the impedance measurement. And then you can see when we which we show the electrolyte film that shows the highest performance actually have a very high quality. You can see like the small part is magnified here. You can see a very low the ohmic resistance, and then also good surface quality. So you also have the good catalytic activity because you have the good surface interface between the catalyst and also the electrolyte. So we have figured out that we can find some good condition, okay, to make a dense and then good property, good electrolyte from this experiment. Now we move on to the next problem, which make the oxygen electrode. Okay, this is much more complicated than the fabrication of the electrolyte, because the material itself is very complicated. It's made of LSCF, okay, lanthanum, strontium, cobalt, ferrite, and then also we have to mix the ceria because it's basically making more the catalytic surface by mixing the ionic conductor. Okay, so basically it's made of like 1, 2, 3, 4, 5, 6. Okay, 6 different metal oxide. So it's a complicated process. So for this we use a different strategy, and then I will explain it shortly. Okay. I think I explained this in before, but the requirement of the oxygen electrolyte is basically at high temperature, the strontium usually forms the secondary phase, react with the zirconia, which is electrolyte, and then produce the secondary material, which inhibit the operation, inhibit the operation of the oxides. Yeah? And also there is when we have these secondary materials and then move of the strontium, it breaks the pore structure, and then we need a good passage. Okay, we need a good passage in the electrode to provide steam and the oxygen and the oxygen. Okay, so we made this kind of the low temperature operation structure by sputtering, and then what we tried is we use so-called the co-sputtering. Okay, so we are having the one target which is the LSCF. Okay, which is the crystallized, well crystallized target, and then we use GDC alloy target. So it's basically metal, and then these two materials, okay, two targets, co-sputtered at the same time to produce this mixture of LRCF and GDC electrode. Sorry. So that there has been some report, okay, about the co-sputtering, and then in this in this reference, the LSCF target and then zirconia YSC target has been co-sputtered, and it produced this beautiful columnar structure, which shows a very high performance for the solid oxide fuel cell. So we also referring this material. We are now changing this yttrium and zirconia, switching this with gadolinium and cerium, and then we use that in not the fuel cell mode, but we also try that in solid oxide electrolyzer mode. So what's important is basically the cartoon here. We are the LSCF and then GDC. This is a metal target, so we use the DC power. And then this is the oxide target, so we have to use the RF power. So it's RF, and then these are co-sputtered. Okay, and then the important parameter in this co-sputtering process is basically the power ratio between these two targets. So because when you change the power, it changes the deposition rate. Okay, so that means if you change the deposition rate, it will change the ratio between these LSCF and then GDC material. So ratio of these two material can be controlled by employing these different ratio of these powers. So we have tried several cases here using changing the ratio of the power, and then also we use this have some distance. Okay, so we fix the distance, and then also we have some this so-called the glanced angle, the oblique angle, the deposition. Okay, and then also this the rotating targets. All of them is done. Okay, also in this process too. But the important thing is we use the co-sputtering technique. And then this example shows the SEM image of the different ratio, okay, of the power, okay, the case of the different ratio of the powers, and then it's not really easy to observe any big differences between these different powered the materials, different power deposition, but there are some slight changes, okay, on these microstructures, you can see, but it's very difficult to predict which will have the best performance just by looking at the observation. So, but at least we have to make sure, okay, that all these materials, because we have like 6 materials, okay, mixed together, okay, so all these materials exist, okay, as we wanted in this electrode layer. So it's the TM image, and then we have the EDS analysis, and then you can see the gadolinium, lanthanum, cobalt, ferrite, strontium, cerium, and oxygen. Okay, this oxide all exist. Okay, as you want it in this electrode structure. And then this is the test, okay, of the different the composition, the different electrode having different composition, the power ratio, or we'd say the composition of the LSCF versus GDC. You can see it's very difficult. There's not much difference in the performance-wise, but if you look at the impedance, okay, analysis of these different materials, you can somewhat notice some changes. Okay, so what we are looking for here is actually the smallest, okay, smallest the catalytic, okay, catalytic resistance. Okay, so we need this low Faraday resistance, and then it turns out that these two cases, like when we mix the GDC at 60 watt power or the 80 watt power, shows some good small size Faraday resistance. Okay, so we concluded that these two cases shows the best performance, and then especially when you have the 180, okay, the power ratio, sputtering power ratio gives us the smallest, okay, the Faraday resistance in this case. So we best suit to use this the power ratio in our the vacuum chamber. Okay. Okay, so all these are with all these informations. Okay, everything's aligned together, and then also we made another cell, and then in this case we changed in this experiment we changed basically the thickness, okay, thickness of the electrode, because if it is too thick, okay, basically if it's too thick, then there will be more resistance when the oxygen, okay, oxygen gases have to pass through thicker layer. So we expect there will be some performance degradation. And then if it's too thin, okay, then the catalyst loading is too small. Okay, so we are trying to find some good trade-offs, okay, trade-off point between the thickness, and we observe that if it's thin, okay, there is the oxygen goes through a lot, but there is some problems of this low voltage, okay, and then if it's too thick, also the performance degraded, because the oxygen diffusion through the electrode, okay, is not good in this case. Okay, so we also like observe this kind of some information, okay, about how to control the thickness. Okay, and then basically just combining the best, okay, the case best structure, and then the conditions of the deposition process. Then we made so-called this complete cell using the nickel or nickel the electrode, and then YSC electrolyte, and then also the LSCF electrode. Can all those combined, and then we operate them in reversible mode. So again the right side is the fuel cell mode, and the left side here is the electrolysis mode. So when you make hydrogen on left side, and you make electricity on the right side. And then in here, we change the temperature. Okay, so something like our reference point is 500 Celsius here. And then we change the temperature to 550 or even the 450. So you can see the 550 typically generates better performance because it improves the ohmic resistance. Okay, it decreases the ohmic resistance of the electrolyte at high temperature, so performance improves. But even at the 500 or even at the 450, okay, you can still observe the fairly good performance, both on the fuel cell mode or the electrolysis cell mode. Okay, so both of cases it can operate well really at the low temperature, something like around 500 Celsius. So we found that this type of thin film structure, and then all this physical vapor deposition process actually can make a working, successfully working electrode and electrolyte structure for the solid oxide cells. Okay, so just for comparison, these types of thin film structure, is compared with the performance from the other types of other cells, which operate near the 500 Celsius from the reference. That there are a fair amount of good researches, which has been published by the other people, and then our result is actually one of the best or some comparable to the best result, especially in the near the 500 Celsius range. So the property of the electrode or the electrolyte material, property of those materials are fairly good, even though we use the so-called the physical vapor deposition process or sputtering process, and then the co-sputtering or this reactive sputtering is can be employed effectively, to make the working electrolyte and the electrode for the solid oxide cells. Okay, thank you for listening, and then I think this is the end of my talk. And then if you have any questions, I think I can answer them. Right now. You can. Yes, there is the question. XR result. With the rotation rate. Oh, okay. That's a very good question. I think I expected that, Christianity, but didn't. So actually, that's a very good question, and I don't really have clear answer. Also, I searched it through some references, but there is almost no reference about the observing the effect in these two parameters together. So actually that's a very difficult question to answer, but my general idea is usually when you need I think we usually need a little bit slight high speed, to sort of more uniformly, deposit the material, and then also the distance and then the power. I didn't mention it in my talk, but when you have the higher power or the short distance, that means there the sticking coefficient is low, but the heating speed, heating speed of the particle is large, and then what we guess is when you have the higher heating speed, so that means when you have the short distance, we think it with a higher speed, higher heating speed, higher energy bombardment can help the formation of the crystallinity. So it's something very difficult. If it's this heating speed have to be well matched with the crystallinity, the bonding energy to form the crystal energy. And then if you also change the speed, actually it's changing the speed of the bombardment of the atoms or plasma, because we are also mechanically changing the speed of the rotation. So actually, this is distance and then speed is actually some coupled phenomena that we think, and then somehow we made a good some sweet spot, sweet spot for the deposition. But it's the chamber size, chamber distance, and then also the angles. And then also this is the heated substrate. So temperature is depends on this. So it's a more like complicated process. And then regarding your question, we are still investigating, but it's I'd say a little bit complicated. So that's what my answer. And then also the next question is the lantern LSCF, LSCF perovskite material. That's very good question, actually. That's very good question. So we ask the questions about the perovskite material. So as you all know, the perovskite material is very difficult to control, especially to get the crystallinity. So we before we trying this, we didn't know that this method will work or not. Okay, because this LCF after transferring from this target to the substrate using the atomization and the plasma, and then it's redeposited. So we didn't know this will work or not, but it's somehow controlling the RF the sputtering power. We could transfer this perovskite structure from basically from the target to the substrate. So the one key is actually the temperature. Okay, so probably when we atomize, and then it probably, because we are having the something like high 500 Celsius, which is somewhat high temperature for applying the high temperature for the substrate. So we think we are sort of forming, okay, also forming the crystal, the perovskite structure again in this the substrate. So I think your question in the future, I think it's manageable. I just say the controlling the structure is what we found is manageable. So I think we can have many possibility of working with the LRCF material. Okay, so that will be my answer to the question. And then another question is why increasing rotating speed? Okay, get stress decreased. Okay, that's also a good question. That's a generally observed phenomena. Okay, some observation we generally observe. When you have the rotating speed, okay, rotating speed, that means the deposition angle, okay, changes more faster. Versus if you make extremely slow, okay, and then the deposition direction is more fixed. So that means we are like sort of making this force, okay, the deposition this when the plasma hit the substrate, then force is right, the changes into the all direction. Okay, so that's why the rotation speed, okay, increases, and then typically the stress relieves because we're changing the direction of the force more frequently, okay, instead of having the slowly. Okay, although there is some limitation, right? You cannot make this too fast, okay, too fast. So this only it is a valid statement only under certain speed, only under this certain rotation speed. This argument is valid. If it's too fast, this argument does not work. But at least some range this range that we are discussing, at least this argument is, I'd say, applies, true in this case. Okay. Okay, and then I think there's another question. Okay. And then what are the size of target? Oh, okay. Okay. So regarding the target, that's a very good question. We do not make the target. Okay, so we buy the target, but the target size we use is about 2 inch. So it's a 2.5 centimeter target. So if it's too big, I think you will have some problems of the sintering, okay, because the oxide have to be dense. We even though we order it, it have to be needs the crystallinity, also have the very high density, something like larger than 95% the density. Okay, so we order the target, but we have a good source, and then we use the so-called high quality target. And then the surface temperature is typically we use something like 500 Celsius, because that helps, especially like some structures like I mentioned it before, but especially structures like perovskite. It really helps to maintain the crystallinity. Okay, when you apply the typically about 400 or 500 Celsius for the substrate temperature. I think that may answer all the questions. Okay. Any more questions from the audience? Okay. Okay, I think if not, yeah, I have all answered all questions. I think you you asked really good questions. I think, and then hopefully my answer helped all these clear up all your the questions. Okay, thank you very much, and then thank you for having me today, and then hope you also have good luck on all your the research progress. Okay, so I think I can wrap up my talk. Okay. Thank you very much. Thank you.